What I wanted to speak to you about is metrology, measurement, and the structure of metrology, and also how it was applied. I'm going to start telling you, in the course of the talk, I'll be telling you what it actually isn't, because naturally before we discovered just exactly how it was structured, then we made lots of mistakes, lots of errors, made assumptions. And you can see people still doing that today. So, I'll be starting off by telling you what the subject actually isn't. Now, what the subject actually is about measurement. I mean, measurement is the determination of any magnitude in relation to a fixed magnitude that's regarded as a standard. Well, these magnitudes must be fixed. There's a great deal of energy and thought gone into thinking like Pythagorean thought and Platonic thought, that the numbers pre-exist everything. And the only fixed thing you find, the only constant in the universe, is in actual fact number. And number is purely abstract, so the whole thing is about this wonderful abstraction. And yet it's the foundation of all of our arts and sciences. It's this guy who first, John Michel, my dear friend and mentor, who infected me with the subject. He's the guy who provided the tools, and he was the first one throughout history who provided the absolute tools in order to start the decipherment of metrology. Now, this is us in fairly typical pose. This would have been about 2004. When we first began, it was around 1967, and John, when I first met him, was writing this book, View Over Atlantis, and this book was instrumental in kicking off the whole movement of interest in the ancient world that still obsesses many, many people today. But John Michel was instrumental in starting this off, and he's righteously looked upon as the sort of father of the study, because he was a very thorough investigator into all kinds of phenomena. But he was also what you might call a mystic, if you can say a mystic is merely somebody who's very intuitive. And it's John's intuition that led him to inhabit realms that normal people don't inhabit. He through his reading of his voluminous reading, he was inspired by Bly Bond's Gematria and William Sterling's The Canon to see an order that ran through all classes of phenomena that they were instrumental in writing up. Well, in the course of this work, he began to get an interest in metrology. The study of Gematria is the numerical values of words, even phrases and whole sentences will have a numerical value, the letters being the numbers. So every word, here is Hermes, here is phallus, here is pyramid, and the way. And if you add all these letters together, it equals something else of significance. In this case, it's Jesus Christ. Well, the Gnostic scriptures were all about Jesus Christ. So it was a study in knowledge. Unfortunately, it was replaced by a study of faith, but we won't go into that. It's not the purpose here today. This is rather a romantic way that he saw it. I mean, he soon gave up this sort of thing, but it inspired him in the first place, and consequently it inspired us. This is a very typical thing from View Over Atlantis. This is an alignment between Stonehenge, Old Sarum, and the cathedral in Salisbury, and a megalithic ring further up in the hills just above Salisbury. And this is where he first noticed that they were using, or appeared to be using, units that we're familiar with. Sarum to Stonehenge, for example, is 6 miles. Old Sarum to the Chapter House of Salisbury which is here, is a further 2 miles, and there's an old chapel in Salisbury that's exactly 440 yards. Well, this is 2 furlongs, and then from this chapel to Clearbury Ring is a further 2 miles. He's given it as the distance from the Henge to Clearbury equals 90 furlongs. Well, it's not actually; it's 82. But I don't know how he managed that. But this is typical of metrology in those days. It was all very approximate because nobody had exactly defined it, and it turned out that this turned out to be our job. But this is typical of the stuff that's in view over Atlantis and how he first got interested in metrology. Here it came to the height of absurdity. His findings of the Great Pyramid. It was still enough to inspire us all, but he soon dropped all this stuff, which is why he wrote the definitive book later on, The New View over Atlantis, where he weeded out all the stuff that was erroneous in the first place. But this is how he saw a progression. This, for example, is what he envisaged as being the capstone of the pyramid. It's a tiny thing, it's 5 cubic inches, and he assumed it was a golden pyramidion tipped with a seed, and the pyramid, he worked out a great cubit of 55 cubits, another nonsense measurement, but anybody could make anything up about metrology in those days. There was nothing solidly known about it, right down to the fine detail, up to the huge geographic distances. Very little was known about metrology with any certainty, and we'll come to this. But it was a multiplication by a factor of 56 squared, that is the overall height of the pyramid. And the side of the base then will be 8 great cubits, and the base times 56 is 8 miles. So therefore the gold apex, this little gold apex thing, 5 cubic inches, multiplied by 56 to the power of 5, will equal the perimeter of the Earth as represented by the side of the base of the pyramid. Total nonsense. The whole thing was total nonsense. But we had to start somewhere, and that's where John started. Enough to inspire everybody, but also enough to inspire the powers that be, that he was full of nonsense, which of course he wasn't. This is when, and this is another thing that he also, in the course of his writing, the follow-up book, which was The City of Revelation, where he got far more objective in this book about the structure of metrology. This is a Riemann, and that's a 20-digit measurement. And this is a Roman Riemann, yeah, so, and the square root 2 times the Roman Riemann, then he says it was a Royal Egyptian cubit, 1.72 feet. 1.72 feet is not a Royal Egyptian cubit. And 2.107 feet, then that's the Riemann times square root 3 is the Palestinian cubit. There is a Palestinian cubit very close to that, but it's not accurately that. And this is the thing about metrology. It's very, very precise. And a miss is a miss. There's nothing close to about metrology, because it's a very integrated structure that connects by unit fractions, and there is no room with unit fractions for anything near enough. Now all this is near enough, and that was the state of play in those days. I still see this diagram being used to illustrate the connections between metrology, and it's another piece of nonsense. Now this, I was separated from John then about this time, but I was kind of infected by the whole curiosity about the study, and I began to form my own cosmologies, just as John had done. But I lived in the States for some 4 years and never had any contact with John, but I still continued the study all the time, knowing that somehow the Great Pyramid would hold the keys to the decipherment. This was a very inspiring book by Peter Tompkins. It's a collection of everybody's view of the pyramid over the years, and it's got some very objective stuff in there that was a great assistance to me and to John. When I got back, John had also found the book to be very helpful, and it was particularly the appendix to this book written by Livio Stecchini. And this is the first time I'd come across what you might call a professional metrologist and his views of measurement systems. When I got back from the States, John was then busily writing City of Revelation. And he'd come up with this. Now, this is as important as any of the Platonic solids, Euclidean diagrams, the axioms of geometry. This is as important as any discovery by the ancient Greeks or geometers ever since. What he'd actually done, he'd taken two circles and put a box around them, and this was the size of the moon, and this was the size of the Earth in proportion. Well, we were having a pint one day in a local pub near where he lived, and he was actually drawing this in the margin of the Evening Standard, trying to tell me how this squared the circle. Because if you take the centre of that circle, which represents the moon, and the centre of that circle, which represents the Earth, and call that a diameter, a radius rather, and you drew the circle indicated by that radius, then it would be of the same perimeter as the square. In fact, it's the age-old problem of how you square the circle. Now, when he was actually doing this, he just gave a start, and he said, Christ, I wonder if it is. And this is what he'd noticed. And he hadn't noticed this before. This is a Pythagorean triangle in the corner of these two squares. Now, this is truly remarkable, because the Pythagorean triangle of 3, 4, 5 is considered to be the building block of the universe, according to the old geometers' Platonic thought, one thing and another. And so this then became the departure point to create this diagram after he'd noticed that, because anybody can draw a 3, 4, 5 triangle. Then you square the base, corresponding triangle on the other side, then that means that's 11. That's 3, that's 4, that's 5, therefore that's 11. So the perimeter is 44 of both the circle you would draw from it and the square. And this is how it develops. This is how you get the pure numbers. And this is the seeds of metrology, because it's pure number. And number pre-existed everything. You know, it's the only constant there is in the universe. And there you have 7, 11, 44, 44, all coming from a 3, 4, 5 triangle. This then is the profile of the Great Pyramid, because the Great Pyramid, in no uncertain terms, is built to this particular ratio of 7 by 11, 7 height, 11 side of base. This is then the foundation diagram for the creation of the diagram of the New Jerusalem, which is the description by St. John the Divine. And it was pointed out to him by an angel, or guides as they call them, who explained all the dimensions to him, holding a measuring reed. Yeah? And that you've got the same story in Ezekiel. And it's quite a common scriptural story, is the description of the temple being described by angelic beings. Then this was the foundation of the objective metrology. I mean, this is after we'd made all our mistakes, when John was actually, we'll just skip back a bit. I mean, this is what intrigued me when we were separated by the ocean. I was fixed on the tip of the pyramid, and I wondered what would be a 56th part of this small pyramidion, and so therefore it would be 56 cubed, or 175,616, into the height of the pyramid. Now, I noticed that this tiny little seed, the 56th part of this, would then be almost it would be a 365th of an English foot. and damn, you know, I was caught up in the same madness. I began to see everything about metrology in terms of time measurements, because the English foot then, this, would then have 365.2422 divisions, and it would be representative of the solar year. Then it would enable you to calculate the height of the pyramid, because it would be 56 cubes times, you know, this tiny seed, which would be 356 part of there'd be approximately a 32nd of an inch, you know, you know, that's a common division that we're all still familiar with, or were, until the hideous meter took it over. But I began to see everything in terms of the linear distances being regular numbers of days. It's a non-starter really, because a day has to be a variable, because the days years ago were rather longer than they are now, you know, so or rather shorter rather. They're slowing down, you know, as time goes by. So you cannot have a day or even a year as a fixed. But I didn't know that, because the Roman Riemann is where John started with one of his nonsense of square roots being related to numbers and regular progressions. Square roots are irrational, so they can't fit into a number system either, or a numerical system, not without adjustment or approximations, and some of these are very valid, but the pure roots then don't fit into any metrological system at all. But I saw that the Roman Riemann is where John started with his progression of roots. I saw that was 444 days. If the English foot was 365 and a quarter days, you know, and so I carried on with the same sort of nonsense. And it enabled me to give a value for the Great Pyramid of 480.82067 feet, and that's suitably close to any of the figures that were promulgated for the pyramid, or given as like sort of fixed units by people who had no business doing anything of the sort. Nothing at all was known about the exact definitions of metrology in those days, and this is but yesterday. Now, if it's 480.82067 feet, then it enabled me to give a value to the Royal Egyptian cubit of 1.7172166 feet, and this is suitably close to all of the different values that are forwarded to the Royal Egyptian cubit. But I thought I'd found how the values were fixed. Now, when I got back to England, and I had all these theories, I ran them by John. See, the first thing I did, and strangely, he'd been worrying about exactly the same sort of thing. We were separated by thousands of miles and great distance in time, and yet we were both beavering away at the same problem, like the value of the Royal Egyptian cubit, its exact length and its definition. I thought he'd be rather pleased with my sort of theories about the number of days, because it was so, you know, it fitted the facts so well. However, he was a lot less than enthusiastic, and he was very non-committal. He was obviously shaping up his own ideas, and lo and behold, a couple of years later, he walked through my door when I lived in Wales at the time. He walked into my farmhouse, and he looked rather smug, and he threw this down on the table and said, "Oh, I thought you might enjoy this." You know? And this is the most succinct thing. It was the key to the whole door, and he'd actually cracked it. I'm not saying I felt resentful that he beat me to it or anything like that. In actual fact, with my line of thinking and reasoning, I never would have found it without John pointing out various key things. Now, I'll point out some of the things now that John found that put the whole subject onto a scientific basis, and really was a foundation for the expansion of the subject. He did things in his conclusions in this book. He'd done things that nobody had ever done before in the field of metrology. That is, to exactly define measurements. Because previously, I mean, even William Petrie, one of the greatest metrologists and a great surveyor, even if he was explaining what a Royal Egyptian cubit was, he'd have to give it within parameters. He couldn't say it was exactly that or exactly that. He'd have to say it was plus or minus, very fractionally, but like, and that was the same all the way through metrology. No ancient unit had been given exactly. Now this is what John changed about the whole study, because he came up with, this is one of the things he came up with in this book, that the values of the Roman foot, the Greek foot, the Egyptian foot, and what he had to term the polar foot and the sacred Jewish. And he found that there was a separation between them of exactly 175 to 176. So that was 175 to 176, a unit fraction integration. And he found that these here, this is the Greek foot, which is 25 to 24 of the Roman. He'd exactly identified these values, and he'd tied them to lengths of the degree. I mean, 1.008 feet is a geographic foot is a 360,000th of the geographic degree. So 360,000 times 1.008 is 362,880, and this is the length of the degree at about 10 degrees. So he called this tropical, and then this is the degree at about level where we live here. This is southern England. This is the degree at around 51 degrees, and it's 101.376. He'd found examples, you see, of these different feet, all of them, you know, in his various reading. But this is an extremely limited database. And in later times, I could never elicit from him exactly how he'd come to these conclusions, because the more I began to research a thing, he'd hit it on right on the button. He got it exactly right, and he never remembered how he'd done it. I guess this is how inspiration gets you, you know. But this is a measure of his genius, really. But I mean, he identified the Royal Egyptian cube as 1.7181818, and that's exactly what it is. But you saw that these 175 to 176 differences were apparent in all of these. Now, he had to term this polar, this particular measure, because it is compatible with the polar diameter of the Earth. I mean, he went on to define the mean radius of the Earth and the polar radius of the Earth as separated by the fractions 441 to 440, and it held good. And he never knew how he came to these conclusions, but he got it exactly right, and that's what nobody else had ever done, exactly defined these measures. And these he called northern values and these tropical values, because this is at 51 degrees north, this is at 10 degrees north. He actually labelled, under this terminology, different units from different cultures, and this had never been done before. And this was another great step forward in metrology, and the whole subject went into sort of a hiatus then for about 10 years. We thought it was done with, but still nagging in the back of my mind, and indeed nagging in the back of John's mind. We knew that it was far from complete. This was just the key to the door. And that's when I picked it up again. And I saw something not quite right with this. And what it was, I noticed that there's a unit fraction connection here. We know this is 24 to 25 between the Roman and the Greek. But then I began to see with the Royal Egyptian that this looked as if it was out of line, because this Royal Egyptian foot of 1.152 is exactly 8 if that's 7. So there's a unit fraction connection there, 8 to 7. Then I also noticed that what he's had to term polar, I wish I had time to go into explaining to you exactly how he arrived at this polar value, but it was the best fit at Stonehenge. At this value, it exactly fit the inner diameter and the outer diameter of the lintel rings, and both perimeters in whole numbers. And this is why he called it a polar measure, because it's compatible with the polar radius of the Earth. But that's not what I want to continue with now. I noticed this was out of line. So I wonder what would happen if I budged this across here, which I duly did. I budged these 2 columns that were here over there, and filled in the gaps, you know, to make. We started with 2 columns, John's polar and tropical, or northern and tropical, and I noticed then that these were all very well attested values of these particular feet, and it was obvious then, having the polar in the right place, that it was 7. It was it was a unit fraction of 6 to 7 of the Royal Egyptian. So the value, the terminology polar that he had to invent to explain what it was one of the better known values. It was one of the better known measurements in the whole of history. It is in fact the common Egyptian foot, and the common Egyptian foot relates to the Royal Egyptian, and with this as 6 to 7, that then with this new arrangement of the columns that I'd instigated, that then you saw it was indeed 6 to 7 with the right column comparisons. And then I noticed here that this was the exact height of the Great Pyramid that it identified, and that holds good, 481.090909 feet. So that's 500 Roman feet of 0.962181818 feet. There are many, many examples of a foot of this exact length, you know, throughout the Ottoman Empire and throughout Europe. Its cubit was used in Holland, and, you know, hundreds of examples of this precise value, 962181818, 500 of them being the exact height of the Great Pyramid. So the height of the Great Pyramid, as well as being 280 Royal Egyptian cubits, is also 500 Roman feet, which is the 10th of the Roman mile. It's a 500-foot stadium. We'll come on to this, because we have 2 kinds of stadium, a 600-foot stadium, a 500-foot stadium. And we have this 5 to 6 relationship with measures. We'll come to this again, but this is known as the surveyor's or builder's cubit is 6 to 5 of the mercantile cubit that's used by the military and one thing and another. Anyway, this did away with John's tropical and northern, and we have yet another column. And the question immediately sprang to mind once I'd made this adjustment and saw the validity of the measures that I uncovered by doing this. The question then arose, where does it stop and start? How many variants are there of the same foot? And as time went by, and I did lots and lots of research, unbelievable amounts of data I gathered from the extremely limited data that John had built this up from. The other mistake he made here was regarding this as a foot. This is much too long to be a foot, and we'll come to this shortly as well. But this is much too long to be a foot. But what he'd done is he'd taken the sacred Jewish cubit and he divided it by 1.5, thinking, but no, you've got 2 foot cubits and you've got 1.5 foot cubits. And this sacred cubit is in fact a 2 foot cubit. And the sacred Jewish cubit is 2 common Greek feet. We'll come to that shortly. But this then is not a foot length. It is in fact, it would be a value of a cubit of, not a sacred Jewish foot, it would be a cubit of, say, the Iberian foot, you know, one of the lesser feet. We save that again. But we were coming on to, where do these variations stop and start? Well, I got it rounded off in the end to like these, what you might call the core values. Now, because we're thinking in terms of the English foot, then the English foot goes in the root position here. I was very fortunate, you know, to be thinking in English feet, because there'd be no other way that it could be deciphered. I mean, if you use millimeters, all of this is invisible. I'll get to that later as well. But here you see, you might call these the core values. There are now 8 variants instead of just the 2 that John came up with. These are the 2 that John had. The standard canonically identified as a Greek foot, and the standard geographically identified as a Greek foot. This comes from the measurement of the Parthenon by Penrose in 1882, and this comes from John Greaves and his measurement of various monuments in Constantinople and in Egypt and in Italy in about 1640, and he'd come back with this, and so John noticed this is 175 to 176, but then that's 175 to 176, and this is how they go, this is how they progress. This is 441 to 440 in the columns, and along the rows it's 175 to 176. So you've got these 2 values of the 440th part and the 175th part, and the combination of the 2 is 1.008. That's the combination of the 2. You can see it here, 175 to 176, 441 to 440. So then you have another important connection in metrology. This is 1 to and it's 125th part. Yeah, so it's a combination of the 2 fractions. And this is why, I'll just explain here why it's so much easier to identify things in terms of the English foot than it is in millimeters. I've just written it up here. The Attic Stadium, the Stadium of Athens, was given as 185 meters. Well, convert that to feet, it's 606.956 feet. And therefore, you know, it's a 600 feet measure. And so you divide by 600 because it's giving you the prefixing number. 185 doesn't give you the prefixing number, if you see what I mean. So you don't know what you're analysing, really, if you're thinking about everything in meters. We'll come to this repeatedly. But 600 divided by that is 1.011593. But here, you see, this must then be a root geographic, because that's 1.011461, it's 224, it goes on for a bit. But you can adjust that to be this, and quite legitimately, because it's a minute fraction. And then it changes your 185 meters to 184.976 meters. No ancient measurement is ever exactly definable in terms of meters or millimeters. It's always going to be a fractured number of millimeters. I'm not saying it's impossible. Some of them will agree in whole numbers of millimeters, but I've never found one. The meter is completely divorced from the systems of antiquity, and it's absolutely useless for metrological analysis. We'll come across this time and time again. Similarly, Eratosthenes' 500-foot stadium. We know he was using a 500-foot stadium and not a 600-foot, as the Greeks were here. It's given us 157 meters. Well, this is 5142857. But by thinking in feet, the prefixing number 5 is there. In meters, it's not, you see. If you came across 157 meters somewhere, it wouldn't register as a 500-foot stadium. But given it's 514, it's obvious it's a 500-foot stadium. And all you've got to do is identify the particular foot. So I was so fortunate in being English of a certain age and being interested in metrology, because nobody else could have done it. Only somebody who thinks in terms of the English foot could have possibly deciphered metrology. As I say, you know, those poor deprived people who think entirely in the metric system are buggered. Now, John had thought that that the 175, 176 fraction was a separation between the length of feet at 10 degrees and the length of feet at 51 degrees, and he thought this was the reason for 175 to 176. But when I got into it, I found that if you have a diameter of 4 feet, and I got this directly from Vitruvius. Vitruvius was a Roman architect who built using ancient Greek principles in his architecture. This was one of his explanations of the Waywiser, as they used to be called. And a Waywiser is like an odometer, it's a milometer. And he said that 4 Roman feet as a diameter will give you 12.5 feet as a perimeter. Now that's only correct if you're using 25/8, it's the pi ratio. Well, this then gives you a whole number, you see. And because you've got 12.5 Roman feet, and the Roman foot is connected to the Greek by 24 to 25, then as well as being 12.5 Roman feet, it's exactly 12 Greek feet. So if you're using the Roman foot of 0.96768, it would then be 12 Greek feet of 101376. In fact, the difference between 25/8 and 22/7, which is what you normally use for pi, is 175 to 176. So there you have an eminently more suitable reason for using this fraction, and it's simply for the maintenance of integers. If you have to work out 4 feet diameters, they're not multiples of 7, so you're going to get a fraction number in the circumference, unless you use the foot the 175th longer in the perimeter than you do in the diameter. So here you've got 4 Roman feet of 0.96768 does indeed equal 12.5 Roman feet of 0.9732096. And this is 175 to 176. Just as 25/8 is 175 to 176 of 22/7. So therefore, this separation in the various feet is for the maintenance of integers in designs. And the 441 to 440 fraction is exactly the same. Here, if you take a canonical number, 360, and you naturally associate that with the perimeter of a circle, it's 360 degrees. But if you say that the perimeter of the circle is 360 English feet, then its diameter then would be 100 rod Egyptian feet of 1.14545454. Now this then is the standard value, but the value of the rod Egyptian foot is 1 1/7 of the English. So 100 root rod Egyptian feet, because this is a root number being the English foot, is 1142857. But it's given that 440 to 441 value in its literal diameter. That is, it's added that fraction. And this is, so you see that both 441 to 440 and 175 to 176 that govern the separations in the values of the various feet also have a very, very practical purpose. I mean, they're not whistling Dixie when they're doing this. They're doing something practical, and this is this beautiful practicality is what underlies the whole system. It makes sense. Anyway, we'll go on from there. This was the next step in the structure of metrology, really. When I'd come up with like the 8 core values of the different feet, John was very, very reluctant to accept it, and he proved most difficult to. The very man who discovered the system wouldn't be budged out of his little narrow paradigm where he'd written the book, and it was with great reluctance that he began to accept, the additions to his work, and the mere fact that it was the inspiration of his work that had formed the foundation of the expansion. He was very reluctant. I remember once he said to me, sort of very begrudgingly, we were sitting around his table one night. He said, he said, I found one of your values last night. I said, did you, John? That's wonderful. So he came around to it, but very slowly, very reluctantly. And this is how I was working on it. Well, I knew from reading Stachini that the Assyrian foot, or he called it the Mycenaean, but terminology is something you've got to watch out for. But it was 15 to 16 of the Roman. And we know the Assyrian then is 9 to 10 of the Greek, and the Romans 24 to 25 of the Greek. And also, according to the governor of Gaul, Nero Claudius Drusus, the Belgic foot was 9 to 8 of the Roman, and this is how the exchange rates for trade were set with the Gauls and Rome. So if you put the Belgic foot in there, that's 9 to 8 of the Roman, then you see it's also 6 to 5 of the Assyrian. You begin to see this fractional integration, always by unit fractions. This integration. So I got what I had to identify the root number, and the Assyrian, the Iberian, the Roman, the Common Egyptian. I just got 12 of them there. There are, in fact, we'll come to this in a minute, there are in fact 19 separate values that you can call foot. Beneath the lower it goes into lesser modules, and above the greater it goes into greater modules. There are 19 values that can be called a mathematical foot. There are anatomical feet, but they're quite different. An anatomical foot would be the length of your actual foot. But what foot length means, what foot means in metrology is basis, and everything's calculated from the foot lengths. So whatever modules you're finding, you convert them to see how many feet they are, or what fraction of a foot they are, and identify the foot. And it's much easier to make the comparisons at the level of the foot. But I gathered all these feet together, and it's an extension of this. The Assyrian and Iberian were 63 to 64, and the Assyrian, as it says up here, was 15 to 16 of the Roman, and so on and so forth. Well, if I've got all 19 of those feet, the bloody table comes over here somewhere, so you can't really see it, you know. So I just used 12 values, and John rather liked that when I came up with this table, and this is where he got involved again. He kind of got over his reluctance to accept this expanded database that I was coming up with, and he got very seriously and involved, and it took him many months. I'll show you the next table that he came up with. It took him many months to compose, and it was a bloody nuisance when he was doing it. I'd get phone calls where he'd speak for hours trying to get the right value, but what he'd noticed, you see, from this table is the prevalence of square numbers that happen. And this is just how metrology works, yeah. You've got 64 is a square number, 16 is a square number, 9 is a square number, 25 is a square number, 49 is a square number, 36 is a square number, 49 again, 25 again, 49 again, 16, 36, 49. And he saw the prevalence of these square numbers, and lo and behold, he came up with this, and this is a major contribution, you know, once again, given by John Michel to metrology. I mean, he really was the founding father of this science. And what is he'd arranged these square numbers together in ascending order. That's 99 to 100, 120 to 121, and saw that those feet that I prepared, and he'd come up with all the potential feet out of this. They start at 0.9 here, which is the smallest foot, and they go up here, which is 1.166. We call that the Russian foot, but it's also one of the values of one of the sacred Jewish feet, you know, so it's, you know, it's a very well provenanced value. And that's the longest measure you can call a foot. That's the shortest measure you can call a foot. And they're all connected through these square numbers. Dozens of other fractions connect them together. But in terms of the English foot, that they're all these. Now you've got some here that are not identified. 6 to 7 of Sumerian. I've found this measure exactly given by John James, a very good architect, in his analysis of the measurements in Chartres Cathedral. But you cannot base, on a single example, you cannot say that that's a value of a foot. It is potentially a value of a foot, and if you found it somewhere, it would be legitimised through this table. Here again, this is again not identified, but it is indeed 6 to 7 of the nipper foot. The nipper foot's here, which is 9 to 8 of the English. There were several others, including this and this, the Persepolitan and the Samian, that were also marked when John first did this table. They were also marked not identified, but in the course of time and research, then they were positively identified. So perhaps these will be positively identified in the course of time, but just rounded things off nicely when John came up with this. And he came up with it at an enormous effort. It took him an age to do it. And what it does is it tells you the cut-off points, the range of feet, the minimum value you can call a foot. Anything less than that goes into the realms of half cubits, or the natural feet. And anything greater than this then goes into the realms of higher values. I mean, John came up with the values and the numbers, but I had to come up with the identifications and say exactly what they were. So this is a true cooperative effort. He took my root tables, expanded on them, and then I came back and explained what he was finding. So we worked together very strongly on this. And this gives you the strictures that you might say are the maximum minimum of what you can call a mathematical foot. Here are those feet, those 19 feet, and this would give you an idea of how proportionately bigger the greater one is. And you can see that sometimes, when they're just 80 to 81 or 120 to 121, how close they are together, here and here, and then how, reasonably spaced out they are. But you can see what they are proportionately. That's the unidentified. I've seen it as registered as cycladic, but like I say, one example is not enough, and that was found in Chartres at that value. Again, not enough to a single example, sorry. But that's what the range of the physical feet look like, and they're all integrated by these unit fractions. That's 9 to 10 of the English, that's 7 to 6 of the English. And the English foot, you see, is happily in the middle of all this, which is why it's ideally suited to classify ancient metrology, because it will be related. It's of equal antiquity to the rest of them. It's the most ideal measure possible to classify other measurements of antiquity. Now then, this table is how you have all the different units, and it's all societies. The foot is the principal unit, and there you have the 16 digits of the foot, and then you have these multiple digits making other values. 40 digits is a beamer, and that's a step because it's 2.5 feet. 2.5 times 16 is 40. 20 digits is a pygon called a riemann in Egypt, and a palimpsest in the Roman, but it's a pygon in the Greek, and that's half of the beamer, and the beamer is a step, 2.5 feet. So the engineers used to go along with the military, and indeed, helping civil engineers as well. There were men called beamatists who used to pace things out in vast distances. They used to pace, and they'd have just like the military do today. They could reckon that the pace would shorten as you're going uphill, lengthen as you're going downhill, and they'd very, very accurately pace out, not accurately surveying accurately, but accurately enough to do all the military planning. If you're moving a lot of people, they were called beamatists, and the beamer is the step. And there, of course, you have the auger, the 6 feet fathom, and then of course you've got the 600 feet stadium. You have a 500 feet stadium. And the 100-foot plethron, we'll see this in a minute. You have all these different units. Now, all the measurement systems in the world, all the ancient measurement systems, all have this same arrangement of numbers of digits and the multiples of the feet units. They all have the same system wherever you go in the world. And of course they're all using the same system of measures anyway, because they're all fractionally integrated by unit fractions. And then you've got all the variations to maintain the integers of whatever design there is in it. There's not a shadow of a doubt, that this same system of measurement was in use all over the world. It's universal, and it goes way, way back into a deep prehistory, because the oldest monuments show its use. So this, in spite of the little differences in the various national systems, I mean, you can take India, you know, and then this is not called cubits or paliastes or dikers or orthodrons. It's called hasta and vista and all that sort of thing. You know, they've got the different names, but they're using exactly the same system with only minor differences. You know, in the Indian, there's a short hasta. It's in fact 14 digits that go between there and there. And in fact, there's one they've left out here that's 18 digits. You know, so this is not complete by any means. The similarities so far outweigh the differences with all the different measurement systems throughout the world that you can state quite categorically that they're all using the identical system of measurement universally. It all stems from the human body naturally, out of convenience. All those measures we've just seen, they're all there. Oh, there's the 14-digit measurement, yeah. Plus the 10 digits, you've got the 14 digits and the 10 digits, which is 24 digits, which is the cubit. And this is how they come into the hands, the 8 digits, 12-digit span, 10-digit palm, 4-digit palm, 4-digit hand, 4-inch hand, which is also sometimes registered as 5 digits. But this, we'll have to come back to that in a minute, because that is just the most inspired diagram. It's supposed to be based on Vitruvius by Da Vinci. It's called Vitruvian Man, but I think somehow he had a lot more help with it than Vitruvius' description. I think the way Da Vinci's drawn that is just a little bit too good to be true. We'll come on to that at some point. But this is how the various units relate to the human body. Well, of course they do. And there's nothing arbitrary or sloppy about this. This is inspired. I mean, for the ultimate convenience for the measures of a man, shouldn't they come from a man's body? Which of course they do, but then they reach geographic proportions and all that sort of thing. Here is Da Vinci's Man. Now what I've done is I've put Jean-Michel's, this is just to show you the integration of metrology, how it does integrate through the human body. And it, of course, like I say, it goes off to geographic proportions. This is the size of the Earth in John's original diagram. This is the size of the Moon. This is the 3, 4, 5 triangle. And it's all this is built around a square that we know is 6 feet, because canonical man is 6 feet tall. Every man is 6 feet tall in one or the other of these feet. So it's proportion we're looking at here. And this is just so damn perfect. And I actually did this because I was looking for what is the centre of a man? Where is the circle struck from? Da Vinci struck his circle, which is this circle. Where did he strike it from? It's supposed to be related to the phi ratio, which would be the length between the top of his head and his navel. It's supposed to be the phi ratio, but I found that it's more like the pi ratio, because if you take the 6 feet, I've given it 144 divisions there, so each is ½ an inch exactly. Then Da Vinci's navel, his centre, is not in fact 55 to 89, which is what it would be if it was the phi ratio. It is in fact 56 to 88, and that's half pi. So I believe man is designed to the pi ratio and not the phi ratio. That's a digression. But taken from this 6 foot overall length, this is the fathom, the height of the man, then you can extrapolate all the rest of the geometry here. Da Vinci's square, if it's 6 Greek feet to 24 Greek feet around, then his circle is 24 Roman feet around. So it's that good. Da Vinci got it that good, and it's a job to see how he did that just by, from somebody else's description. It looks, like I say, a little bit too perfect. 24 Roman feet and 24 Greek feet. And Da Vinci was indeed, at one point, we know from Girolamo Cardano, who was a friend of his, much younger, but they were in fact seeking what was known as the mensura perpetua, and that's the basic unit that governed all others. I mean, they knew it existed. Strange it turned out to be the English foot, but they were pretty close to it. But they thought this was one of the values of the Roman foot, of course. But in actual fact, all this math works out perfectly if it's in fact 6 English feet, and that is the canonical height of a man. And then all the other things, this is then a Sumerian cubit. This is a Sumerian 2-foot cubit. This is then a Sumerian step of 2.5 feet, and so on and so forth. And the value it gives you taken from this is 1.090909 feet. You know, it's one of the measures we've already come across. And then the English foot, then the anatomical foot of Da Vinci's man, if he's 6 English feet tall, is exactly half a Royal Egyptian cubit. So this is how measures, they don't just simply integrate through a unit fraction connection with all of them. They all actually integrate through the human body, you know. Any one of them, we've got to paint this subject with broad brushstrokes, because I could stick around here and talk about this all day, but we'll press on. This then is Da Vinci's man in motion, Vitruvian man. You see, his step is 2.5 feet, as we've already seen from the beamer, and then his pace then is 5 feet. So, man in motion is measured in paces of 5 feet, and the static man of the canonical numbers is 6 feet. Now, the 6 governs circles, so it's the number used by surveyors and architects and astronomers. They would be using the 6 values, and their miles would be 6,000 feet miles. Yeah. We're dividing up the heavens into a sexagesimal system. The traveller and the merchant and the military then, of course, would be thinking more of a 5 feet measurement, because they've got to pace things out. I mean, they've got to work out journeys over the earth. I mean, they're not navigators on the sea, so they're using the 5 feet measurement. So all these measures are of utmost convenience for the task in hand. And this is a 5 foot measurement. 1,000 paces is a mile. So, you know, this is both static and motion. It governs the 2 principal values, which relates 5 to 6, and this 5 to 6 relationship runs through all of metrology. This, then, we're going to get on to the application of these measurements using the rules that we've already seen that are laid down, you know, from John Michel's diagram of the of how you draw the circle squared and how the units that come out of it are spontaneous. That's it about all these units. They're all sort of spontaneous in a way. You know, there's nothing contrived about all this. It's just what's there. You know, I rather like the idea of a abstract number. you know, just being there. It's a bit like one of my favourite quotes is by the Dalai Lama, and he said that when the Big Bang happened and the universe came into existence, the universe found everything already here. Anyway, that's a bit like number. It is pre-existing. The birth of the universe is not a birth per se, it's a transition from one state to another. So, you know, the laws of physics are there all the time, and so is number itself. That's a digression. This, we've been through this is where the measurements start. This is 1.008 feet, and this then, at 176 to 175 of that, is here at 50 degrees. And this would have been John Michel's original northern and tropical units. But there's several things happening in between. We've already identified this. This would be the length of the degree, at around 38 degrees there. And this is where Delphi is. And there you get Greek geographic law that comes into play there, because at Delphi, the omphalos of Delphi, the stone, is reputed to be the point where Zeus released the eagles that flew in opposite directions around the world and then met back up. So he called that the centre of the world. And everywhere you get an omphalos put down at the centre of every nation is the centre of their world. And this would be the value of the foot there, which is there. And you can see how all these fractions then link up these geographic degrees here, that this is not one of the canonical feet, but it's 441 to 440 of this. And this is the exact northern tip of Egypt. And this is a very significant number that we don't have time to pursue, or I haven't included it in this talk, but it's another thing that's well worth a talk on its own, is the value of this particular foot of this degree. It's a whole can of worms in there, but that's not primarily what we're here to talk about. We're just painting broad brushstrokes and not concentrating on any one particular thing, just the general structure. As I say, that is rather coincidentally, if you took the polar diameter of the Earth and you multiplied it by 20^7 to get the length of the degree, this would be the length of the degree, 364,126.06 feet, which is 360,000 feet of 1.0114612. So that's using the shorter polar radius that would give you that exact number. And if you use the mean radius of the Earth, and that's C to D, 440 to 441 of this mean, and this mean rate, this would be the length of the degree calculated from the mean radius of the Earth. And the mean radius of the Earth is 20901.880, and the mean radius would be right here. And that's very, very typical, because it's all about geometry, and geometry is Earth measure. This is 1, 2, 3. So the difference of this would be 441 to 440 of that, the polar radius. And then the equatorial radius would be half of that on top of that. So it would be half of 441 to 440. It would be 883 to 882. So here you have then the Earth divided up into 3 principal radii. This would be 880, this would be 882, and this would be 883. So the geoid is envisaged very simply. Nowadays, if you consult any geoid to give you the dimensions of the Earth, they'll all give you a different answer, and they all give you perfectly good reasons why they do, but it was just seen that there's no consensus of opinion today exactly how big the Earth was, and yet this is what it was taken to be from the structure of metrology in remote antiquity. 883, 882, 880, a natural progression. And this is how these unit fractions that we've seen then fit geographically onto the size of the Earth. This is not in our tables. This is an extension, as I said. All the values you're finding in the first table are merely the core values. It's extended to this length, and we find this length being in use very practically. Well, before we leave this diagram, I'd just like to point out this value here. This is actually the level of the Arctic Circle, and we'll come to this in due course, but this is where the geographic foot reaches this maximum length. It's 1.008 squared, so it's the square of this value where we started here. We'll move on now to the single fact where the whole of metrology began to make sense to me, and I began to see its purpose and how it was manipulated, and that's this simple little diagram. Once again, we're at the top of the pyramid. Now, I knew the figures 441 to 440 and 175 to 176. Now, this is 441, the pyramid divided by 441 equals the Sumerian foot. And if that's the case, then the base equals a Royal Egyptian cubit. This is the root value of the Royal Egyptian cubit, 1.71428571, and that is the English cubit of 1.5 feet plus its seventh part. So all the Greek cubits plus their seventh part will equal a Royal Egyptian cubit, and this is true across the board. But this is how I saw what was going on with metrology, that you have, in order to maintain integers in all aspects of a design, you have different modules. I mean, that is one Sumerian foot, that's one royal cubit. The Great Pyramid also incorporates the other fraction. If that's the previous diagram, then a pyramid that is the 1/76 part of the overall height of the pyramid would then be this, 2.74090909, and that's 2.5 Sumerian feet. That's a step, and this is the very value that we saw in the original diagram of the pyramid. That would be the 2.5 Sumerian feet. If the height of the pyramid is 3, then this would be the 5. Yeah. If it's 1.5, that's 5. So this is the Pythagorean triangle again, and this then is also a Spanish vara. So it's 3 Spanish feet as well as being 2.5 Sumerian feet, and this is how the integration of metrology works. 432 feet then is a canonical number of this extended, what I might propose would be a double pyramidion on top of the pyramid. Not quite so fanciful as it might seem, but it's just illustrating how the two fractions that govern metrology then, when they're applied to the scale at the Great Pyramid, then form, well-known and proven units of measure. So you'd have 2 pyramidions capping it off. Not so fanciful. These are pyramidions from South Saqqara, so you can see that it's not pure invention. In actual fact, the Egyptians did use devices like this to cap off their pyramids, and there's a perfect example of one. These are in the Cairo Museum, I believe. We'll move on now to more examples of exactly how it was applied, how the measurement system was applied, and the reasons why it exists. This is the dome of the Pantheon, and as you can see, it's designed around a sphere. The bottom half of the sphere that contains the sphere is in actual fact a cylinder, and the top is the dome. So from the oculus to the floor, the diameter of the dome is exactly halfway between the two. Now the diameter of this dome is 142.248. This is calculated. It's given, in millimeters when it's given, or meters rather. But this is the intended number in feet of the diameter of that dome. And in order to find, from the very first diagram that John found, the diameter is 14. When you're describing the circle starting from a departure point of the 345 triangle and drawing all that up. This is universally true. You find it in circles of every description. If you divide the diameter of any circle of the ancient world, be they stone circles, be they the monuments, be they spheres, rotundas, whatever, if you divide the diameter by 14, you get a unit of measurement. Now 142 divided by 14 is 10.16064, and this is a 10 feet measurement. It's 10 Greek feet of that extended value we get with the geographic foot of the Arctic Circle. So it's a 10-foot Roman decempeda if it's in Rome, or the Greek echina was a 10 feet measurement. Pertica, perch, pole, it's a 10 feet measurement. It's universal. But the 14th part of that is then this diameter. Now, if we go on to the floor of the Pantheon, it's built using the Roman foot of 0.96768. The 12 floors are all in increments of this particular value. And Martin Fawkes measured it then in the 18th century, and I measured it in 2008, and it is indeed, it's a foot of 0.96768, and above there's a sliding or a folding bronze rule, rather, of a Roman foot found in Niederberg in Germany, and that is exactly 0.96768. It's given us 29.5 centimetres. And 0.96768 is 29.495 centimetres, so there you go. That is a value of the Roman foot, and this is the one we calculate from the floor of the Pantheon. So we've got these two numbers here now, both writ large in the Pantheon. One is 0.96768 as the Roman foot, one is 0.0106064 as a value of the Greek foot. And we find both of these numbers together here. Now, this man is called Einar Pálsson, and he was a great Icelandic scholar. During his lifetime, he was treated with contempt or derision by his colleagues. He could never legitimize his findings and his claims, and he was a very inspirational man, and he wrote extensively on the Norse culture coming into Iceland and how it adapted to Christianity, and how they were in fact how the land was laid out to specific plans, like the landscape was all divided up, according to their cosmology, and this is around Steinkross. He found that these ancient towns of Iceland were laid out around a circle, and there's nothing there at Steinkross now. It's an empty farmhouse, but there used to be a stone cross there. Obviously, a stone cross is marking a geodetic centre where the surveys would be taken from. But the diameter of this circle is 216,000 Roman feet. Well, this is an incredibly interesting number, because if we take the foot that we've seen in the Pantheon of 0.96768, and we use that with good reason, which we'll come to, then it would equal exactly the 100th part of the mean radius of the Earth. So it's 20901,888. It's a 100th part of that. So, and in fact, this would be also what they call a Spanish Maritime League, because a Spanish Maritime League was 17.5 leagues to the degree. Now, 17.5 times this, the 20901,888, is exactly 17.5 of those would be the degree exactly here up on the Arctic Circle, where we are, where all this is taking place here. And the foot length of that degree is exactly the foot length that we saw in the Pantheon, and the Roman foot we're using to deduce that would be the foot length that we saw on the floor of the Pantheon in Rome. Now, English navigators of the 16th century also used this league, and they classified it as 20,000 feet, in which case they'd be common Greek feet. So you can see that this maritime league was 17.5 times 7,500 Spanish varas, which was their yard measurement. 3 of their feet was called a vara. So That's why it's the Spanish Maritime League. But it would also be 20,000 common Greek feet, and this is what the English mariners used to use. They said that the Spanish League that they used to navigate with was 20,000 feet. They would be common Greek feet. It's recorded they reckon the Earth's meridian to be 6,300 such leagues, and this is exactly right. And this was some 200 years, in about some 200 years before the first definitive survey of the Earth, and yet they knew this, so this was a fact, and they used this in their navigational charts. The incredible thing about this particular measurement, the Spanish Maritime League, is it's also the Royal Egyptian showiness, and the Royal Egyptian showiness was 12,000 Royal Egyptian cubits. So you've got this itinerary measurement that's 40 stadia, it's also given us, and in which case there'd be 40 stadia of Eratosthenes Stadium that he measured the Earth in. So this is a geodetic measurement, and you're getting this from Egypt, and you're getting it from Spain, you're getting it from Britain, and here it is, plain as the nose on your face, identified by Einar Paulsen in Iceland. So this is truly a universal measurement system, and using the same modules of measurement. Right, we'll press on now. This is another way that the measurement system's applied, and this explains to you how the proportion of a building will dictate the module that was selected in its construction. Now this is a local pub that I'm familiar with. It's in Glastonbury. It's called the George and Pilgrim, and I was interested enough to measure it, and it's one of the most pleasant proportions of a room. It's a very nice, comfortable, well-proportioned area, and it's one of the ratios that Palladio used to use. It's a 3:5 ratio, and of course, it's a 3:4 ratio, I beg your pardon. It would then be 5 across its diagonal, so it's like 2, 3, 4, 5 triangles in a way, yeah. But like, if you measure it, which I did, then in terms of the common Greek foot, it's 3 paces. That's 3 5s, 15 Greek feet. And then it's 20 Greek feet that way, so it's 4 paces. So it's a 3:4 room. And then you've got the module that fits 3:4, 3 paces by 4 paces. The diagonal will then be 5 paces. And then we go on to the cross sections. This is a medieval building, so medieval architects were using this. You've got the 3 divisions of this, of the room in as much the cross or support beams. Yeah. Then they would be 1 fathom each. So each of the units on the side is 1 pace, and each of the units there is 1 fathom. But they would be Royal Egyptian fathoms. And you often see the Royal Egyptian cubit used in conjunction with the common Greek foot, because 2 feet of the common Greek would be the sacred cubit that Newton discussed at great length, and it's known to have a 6:5 relationship with the Royal Egyptian cubit. So here it relates as 18 feet to 20 feet, and that's 6:5. So from prehistory, you can see that the medieval builders continued to use the same construction techniques and the same modules of measurement, and the module will be selected to fit the required space in whole numbers. They weren't stuck with one measurement, whereas everything will be a fractured number by using it. They could choose to build in whole numbers, which they did, and this is the purpose of the whole metrological system, is to build in whole numbers and express them, not just whole numbers, but rational numbers that fit the proportions. Now this way you can see the same thing on a monumental scale. This is the second pyramid, G2, and you've got the same 3, 4, 5 triangle here. It's built to that, and Agatharchides stated that the base of this pyramid was 1 stadium in length, and the stadium is referring to was a 600 feet measurement, and this then is 1 stadium 600 Russian feet. So if that's 600 Russian feet, that then is 400 feet, that's 300 feet, that's 500 feet. So that's a plethron. A plethron's a 100 feet measurement, as we saw when we looked at the Greek modules. So you've got a module that fits the proportion, yet again, on this monumental scale, the same as we've seen on the more domestic scale. The same principles being used in the architecture. This is just a few examples of how it's applied. This is Stonehenge. We're more familiar with this. This happens to be a Pythagorean triangle, another Pythagorean triple. The inner Sarsen circle is 100 Roman feet. The outer of the Sarsen lintel circle is 100 common Greek feet. And then this just so happens to be 100 Belgic feet. A rather obvious continuation of the same principles. And then you've got, the regular, the rectangle is a double 10-foot pertica of the standard Belgic foot, because it's 5, 12, 13. So it would be 5, 12, and 13 in terms of that particular module. So the module is chosen from the proportion, yet again, and this is how metrology was used. This is doubly interesting because this is a station stone rectangle at Stonehenge, and that dates to about 3,400 BC. The Sarsen circle was completed about 1800 BC, so there you've got exactly the same principles being used in the further development from the ancient sort of foundations of the thing. You've got the same principles being adhered to, so you've got a continuity of culture that lasts some 2 millennia here. And then we can see the same units, because this 100 Belgic feet, 100 common Egyptian feet rather, of the outer lintel circle is the identical unit that we saw being used in the same manner, using whole numbers, in the George and Pilgrim's Hotel in Glastonbury. So we've got a continuity of culture here, very rigidly adhering to these principles. Again, you see the module was devised from the ratio. I mean, we're just glossing over things here. I mean, we could happily spend a day at Stonehenge pointing out the different, just as we could at the pyramid or any one of the things we dealt with. Well, we could spend a lot of time explaining exactly how it goes on. But this is just broad brush strokes showing you how it's being put together. Now, this is a Persian city, Firuzabad. You can see it has radials, and it also has concentric circles. It's been long ruined. I think Alexander destroyed this, so it goes back to the old Seleucid Empire, But he flooded this, I believe, and it wasn't drained again until about the 8th century or somewhere. But I'm just showing you this because this is in Persian plan of the original city of Baghdad. The Mongols never left one brick upon another. They were responsible for quite a lot of the ancient knowledge being dispersed. But I'm just showing you how whatever the size of the thing, the diameter, the division of a diameter by 14 will give you a recognizable module. And it's very plain here because it's recorded that the dimensions, although Baghdad doesn't exist anymore, the dimensions were recorded in ancient documents. And the scholar of Islamic architecture, Creswell, around 1936, suggests that a cubit of 51.8 centimetres, and this is the cubit of the copper bar of Nippur, which starts from a foot of 1.125 feet. You find this same cubit used all over Egypt. In fact, it's universal. What we call it the cubit of Nippur, because it was the copper bar of Nippur is where they found this, or devised this cubit, and that goes back 2,600 BC, and it's the oldest measuring device known. 51.8 centimetres is indeed the value of this particular cubit. And this was also the unit of construction of Darabgurd, which was another one of those circular cities, but I haven't shown that particular thing. But Firuzabad, was similar. It was a common thing to make circular cities in Persia, and Persian architects were employed to design Baghdad. The perimeter was stated to be an Arabic mile between each of the 4 gates of the city, and the diameter of the city is 2.6395 kilometres. But in order to understand this, you first convert it to feet, 8,659.6363 feet, and 1/14 of this diameter is 618.5454. See, you've got the prefixing number 6 here when it's expressed in English feet. So it's obviously a stadium of some description, simply divided by 600. and it's the common Greek foot of 1.03090909, which is the English foot plus its 36th part, then plus its 4/40th part to achieve the standard level on the tables that we've seen. So this then demonstrates the same principles being used from the very small to the very large. We'll move on from Baghdad here, across the world, just to show you the universality of the measurement. This is known as the Altar of Heaven, and it's in Beijing. It's the Forbidden City is somewhere over here. But you've got this avenue connecting these three important monuments. It's called the Bridge of Cinnabar Steps, the avenue. But this is called the Altar of Heaven, and this is reputed to be the centre, the spiritual centre of China. It's not the geographic centre, but it's the spiritual centre of China. And beyond it, here is the Temple of the Hall of Plenty, and plenty meaning good harvests. And here is the Temple of Heaven, and this is a sacred area that's all connected there. Without going too deeply into it, the Chinese units, they were used in a slightly different way, but there's no doubt about it, they were using the same units of measurement, just to show the universality of the system. In fact, this is designed around the number 9, and this was a sacred number connected with the Huangzhong pitch pipe, and the pitch pipe was the length of a tube that held so many grains of millet and was so many grains of millet long. It was supposed to be the origin of their measurement system, which I strongly doubt, but this is supposed to be a zhang, which is 10 foot. Zhang is their pertica or decempita, but they were using a foot that was 3/4 of a foot. They were using a natural foot here. So this is 9 zhang. So that's 90 of their diminutive feet. This is 15 zhang, and this is 21 zhang. 1 zhang is 5 Royal Egyptian cubits, and it's very exact. So 5 Royal Egyptian cubits was a measurement commonly used in Egypt. It was the length of the cords that we used, or it was knotted at 5 cubic intervals, and we know from Democritus that these people were called harpidon aptai, which means in Egyptian it means rope stretchers, and they were the surveyors. But this is the same unit of design in this, the same length, and as this is built with a on a pattern of 9s and multiples, the 10 foot zhang, the 10 diminutive feet of the half Egyptian cubit, would also be the zhang unit, then would be 9 Roman feet. So this play of 9s that the thing is built around, these are multiples of 9 in the balustrades and everything else, continues on into the measurement system if you know how the measurement system's constructed. So you can see the same principles being used in China. This is just to illustrate the universality of the system. This wall around it's called the Whispering Wall, and it's quite substantial, and a whisper there can be heard on the opposite side as plainly as if you were standing next to the person. And if you clap your hands once there, you get a single echo back. Clap your hands there, you get a double echo. Clap your hands there, you get a triple echo. And a whisper made in the centre of here can only be heard by the person next to you, can't be heard by anybody else, but it will echo back from these balustrades, so you can just whisper something here, and whatever you said will come straight back to you if you're standing in the centre, which is the spiritual centre of China. So there's lots of principles being used here, metrological, musical, and symbolic. This is the Whispering Wall here, the surrounding wall here, and you can see that they're all units. This is the 3 tiers of the Altar of Heaven is 9 zhang, 15 zhang, and 21 zhang. But then this the Whispering Wall would be 39 zhang, and the overall surrounding thing would be 63 zhang. And the length of the wall in terms of the standard Belgic is a 500-foot stadium of the standard Belgic foot, exactly. And alternatively, it's one 600-foot stadium of the standard Assyrian. So that's because these two values are linked by the value 5 to 6. So if you've got a 500-foot measure of one, it's 600-foot measure of the other. There's one other place, there's the running track of Haliesis in Greece, and that also has got two interpretations. It's either 500 feet of the Belgic or it's 600 feet of the standard Assyrian. So there's a connection there in the values with measures that were used in Greece at exactly the same length. So I think that just about wraps it up, really. It's just showing you in broad brushstrokes the universality of the system, and then little details about how it's applied. But the main gist of the message about metrology is it's universal. It's exactly the same system. I mean, how did the Chinese and the Greeks use the same measurement system, and the Egyptians long before either of them? So the mystery remains, but there's lots of mysteries in the ancient world, and it does concern people quite a lot now, the mysterious origins of the ancient world. But this is evidence, this is solid evidence of a universal culture, and this system is so sophisticated and so clever. It makes our SI system of measures look like the crude bludgeon that it actually is. There's no subtlety about it at all. And how it survived through the ages is through comparisons, comparing one measure with the other. And when you've got a unit fractional integration, if you know something is so many of them and so many of them, then it can't change. And if one of them goes wrong, then it's obvious which one has gone wrong, so you can correct them. And this was, I think, the large-scale festivals that went on. It would also be a meeting of the architects and surveyors and the priests to make sure that they were all preserving their units of measurement in the proper manner. And this can only be done by comparison. If they all had one measure, like a metre, then they'd argue like hell about which one was right, you know. But when you can show, well, this is wrong because it's so many of them, and, you know, and so forth. It's such a shame to see this incredibly sophisticated and ancient cultural relic that we preserve perfectly right up to the present day, just to see it thrown aside as if it was no importance at all. And the metric system, I mean, people's traditional and rational and sensible units of measure have been taken away from them, and sometimes brutally, and just thrown aside as if they never existed at all. And they've been given this meter. It's fit only for the use of bankers. It's not fit for a man of imagination to use at all. And this situation is still going on. In Korea now, they've just forbidden their traditional units of sale in flats and apartments and things, and they've made them use square meters instead of the traditional measure that everybody knew, because it was a harmonic with the human body, and it was in actual fact a sort of fathom. So you know, I mean, let's stand up for the foot here. I think it might sound a bit too good to be true, but in actual fact, it's too good to be not true.